Yeah, I won't expect that you would have the good knowledge of fluid dynamics, but that would be helpful for you to get the to clear the interview. See, this is the skills that will help you to understand the ANSYS or any commercial software well, and to understand the CFD. These are required. Also, to understand the physics, you need the fluid dynamics knowledge. That meanwhile
Yes.
you try to cover. Okay.
Okay, sir.
So this is what the main motto of this course. So yeah, these are the two projects I will help you to finish, and these are the things I will teach you. These are the two. Yeah, these are the two projects I'll teach you. And 2D
Okay.
transient, I'll teach in the transient as well as in the steady state. How you can use the mostly we'll use finite difference method. I will tell you what is finite difference method in our upcoming lectures. As I already told you in the course outline time, that there are some numerical techniques are there called finite difference method, finite volume method, and finite element methods. So
Element method.
yes, mostly to solve this 2D transient and steady state heat conduction problem, I will be using a finite difference method. Okay, and also
Okay.
I'll when we will move to the open form course, I'll use the finite volume method. Okay,
Okay,
for
sir.
this problem. And also I will teach, I will show you how the implicit and explicit form of the equation, how is it behaves, and what is the merits and demerits of implicit and explicit form. Also between transient and steady state, we'll see in details. You will do this project, and
Okay,
you
sir.
will make your hand dirty by by doing code by yourself using MATLAB.
So, sir, for first project, I need to study the heat transfer, right?
No, not necessarily, but it will require when you will go for interview. Definitely, they will ask the basic knowledge like what is conductivity, what is Fourier law, all those things. But definitely,
So,
those things they will ask. But for CFD point of view, it is not much required, because here I will be focusing on you should know the mathematics, like how to code, like how to write, use the Gauss-Seidel approach, how to use the Gauss, Jacobi method, and how can use the SOR technique to solve these equations. Okay, mostly it
uh,
would be mathematical, not the physics point of view.
so we will also solve the problem of aerodynamic, right?
Yes, will also, but aerodynamic problem
Be-
I will use open form and ANSYS fluent,
Because my
not with
main
the code.
focus is aerodynamics in CFD.
Yes, yes, I will be teaching that. I will be teaching that in using open form.
Okay, sir.
See, these are the pretty small problem. This 2D heat conduction, these are you can do code by yourself. But when you are moving to do the code for the aerodynamic, let us consider you are making for the flow over an aircraft. It would be pretty complex for you to in the initial stage to write the code. So what you can do, you can go into the open form. Already inside the open form, source code is there. Okay, source code would be there. You can I will help you to in that course to understand those code, and by yourself you can modify. As soon as you will learn the C++, you can modify by yourself. Okay.
Sir, I don't know anything about the C++.
Yes, that needs little bit expertise. But you have to start from here. This course will focus on the making your fundamentals. Okay, this is all idea. And for the aerodynamics that you are saying, yeah, yes, that also I will teach you, but that will be using the open form. See, anyhow, when you are going to the industry, you will be using ANSYS Fluent or any open form or Star System, CFD++, any commercial software. You nowhere they will tell you, okay, you write your own CFD code and they solve. in the MATLAB. Nowhere they will tell you. Okay. So we should focus on the solving these two equations in the MATLAB. Then we can enter into the open form and we can focus how they already have written the code in the source code. I can show you there over.
Sir, okay.
Yeah. So by
Sir,
the end of this course, most of your fundamental concepts that needed for CFD you will be covering. Almost
okay,
everything. Yeah.
sir, there is a project in my head actually. The flight without the control surfaces.
Flight without?
Control surfaces, control surfaces on aircraft, flaps and
Okay.
ailerons, like that. But aircraft will move in any direction without using that, with the help of what we call air only, the ram air.
Mm-hmm. No,
So
I did not get your problem statement
so
correctly. Can you come again?
when we study the airfoil, we can see the pressure on upper surface is higher than lower surface. So that's why the aircraft will get lift.
Yes, pressure on the lower surface is more and pressure on the upper surface is less. That is why it gets lift. Yeah.
Yes. So the velocity of air on the upper surface is more
Yes.
than the lower surface, right?
Yeah, okay.
So if we suck the air through the duct
Mm-hmm.
in the fuselage and move that air over the uh, airfoil or the wing
Okay.
with the help of small slits,
Mm-hmm.
like small gaps. So we can increase the velocity of air of upper surface, right?
Okay. You want to do that CFD analysis, right? CFD analysis of
Yes,
that
yes,
project. Okay. So
yes, yes.
this one I will suggest by the time you will reach at the ANSYS student, you can make this project. The
Yes,
level
yes.
of knowledge I will give you by using the that knowledge you by yourself can do that one. See the first introduction course I will give. This course nowhere will help you to get the job. This course not at all give you the job. Let me be very clear. But this course will make your knowledge at a standalone point. Like you will know how the behind the software the things work. Okay, but
Yes.
that this thing is very much needed. Only doing the answers is nowhere will be useful. That will be like you are using black box. After some time, if you, like a robot, you will be working like a robot. If you are, without understanding CFD, if you are only using answers, then you will be working like a robot. I won't suggest you to go that way.
Okay, sir.
Initially, we will go this course, then we will move to answers or open format for your is like interchangeably we can use. But I will suggest we can go open form then ANSYS plan. So
Okay, sir.
this is the way we can approach. Then you can make yourself a very good fundamental knowledge of CFD.
Okay, sir.
Yeah. So this is the outline of this course. So we can start with our the next presentation. Can you see my screen?
Yes, sir.
Okay. So in this lecture, we will be learning what is CFD and what are the application of CFD. I will give you the brief overview, like a little bit flavor of applications, like where you can use the CFD. Maybe I can show you. Currently, you asked one question about the airfoil, how it can predict the velocity and pressure profile, those portion I might show you those contours that you mentioned. Then we can see the different approaches of studying flow problem. Whenever there is a flow problem, what are the different approaches? Apart from CFD, what are the other approaches available? Those things we will be seeing. Steps involved in the performing CFD simulation of flow problem. Whenever there is a flow problem, when you are doing CFD analysis of that, what are the steps you can follow? What are the steps you can follow? How easy is to set up a CFD simulation? Is it really easy or is it really difficult? That question I will tell you. And a look at the Navier-Stokes equation. Already you have seen the Navier-Stokes equation. Again, I will give the brief intro of the Navier-Stokes equation. Of course, we'll learn in-depth derivation of the Navier-Stokes equation in our upcoming lectures. But I will tell you what are the here I'll tell you what are the terms are there in Navier-Stokes equation and the intuition behind the numerical analysis. Why we need the numerical analysis? What is the intuition? Those things I will be covering.
Okay, sir.
Yeah. Let me clear my screen. Yeah. Okay. So what is CFD? CFD essentially stands for computational fluid dynamics. That you already know. This is the abbreviation. I don't need to explain anything. This is as a computational. I can say this is only adjectives. And this fluid dynamics is the main thing. Like CFD only I can say from English point of view. If I'll say it is only adjective. Uh, it is a technique to simulate fluid flow using computers. Like CFD is a kind of technique. Okay, CFD is a kind of technique. If let's take an example. Through this example, we will try to understand. There is a pipe. At hot liquid is entering. Hot liquid is entering, and this side let us consider some cold liquid are entering, and there is some. This is my outlet. Okay, let us consider this is our problem statement. Now we'll understand what is CFD. It is a technique to simulate fluid flows using computers. This problem statement you can define in your computer and you can simulate to predict if you are giving at 60 degrees Celsius water at 60 degrees Celsius and water at 10 degrees Celsius, what would be your outlet temperature? At outlet, what would be your temperature? If you want to, if you want at certain temperature, it should be come out. How you can? What should be your velocity? What should be your temperature? Yes, of course, this is a small problem. We can solve it by pen and paper. Let us. I just assumed this problem. You can give this input to the CFD, and CFD also can easily predict this one. We solve the fundamental equation that govern fluid flows, like in this fundamental equation, generally Navier-Stokes equation. By solving Navier-Stokes equations, we can solve this we can solve this physics. Okay, this complex physics we can solve using Navier-Stokes equation. So CFD essentially solve the fundamental equations. If someone asks you what are the fundamental equations, you should at a point to tell the Navier-Stokes equation, and you should know what are the terms in Navier-Stokes equation that I will be explaining in our upcoming lectures. Sometimes the physical process are modeled using simplified match equations for saving computational efficiency. See, this is the pretty simple problem. So your CFD, commercial CFD code can easily handle. Let us consider there is a problem like there is a rocket. There is a rocket. It is moving at certain velocity, and this velocity is not constant. It is a function of sinusoidal. Okay, maybe it is a 0.5 Let us consider any sinusoidal function. It is following sine 2 pi ft, like that. Any a naught sine 2 pi ft. Let us consider it is following this path. Okay, this velocity, or maybe it is following this acceleration. So by the now the physics is pretty complex. By adding some by adding some physical process, you have to model this problem using some UDF. There is a concept called UDF, user defined function. Okay, by making that, you can simplify the computational, you can make the computational efficiency, you can simplify that one. Otherwise, if you are not doing that, it would be very difficult, and maybe sometimes impossible to do. Okay, so that one also you can do in CFD, like very complex physics, you can do the simulation. Let us consider you one the IC engine. There is IC engine. Inside the IC engine, combustion is happening. Within a fraction of second, many particulates are forming and again doing the reactions within a fraction of second. If you want to model, you can make it. You can make the simplified. Okay, through the CFD it is possible. If you are doing the experiment, it is not possible. These model interact with our fundamental governing equation. When you are giving this as your, let us consider again, come back to this rocket equation, rocket problem. Your essentially your CFD means, I said, simply solving the Navier-Stokes equation. That's all. When you are solving the Navier-Stokes equation, these models interact with our fundamental governing equation. Means, as I said, you have to give the UDF. These UDF will interact with the fundamental equation. What are the fundamental equation? Those three Navier-Stokes equation: continuity equation, momentum equation, and energy equation. Historically, if you can see, only this momentum equation were called as Navier-Stokes equation. But nowadays, current day, CFD engineer and scientists are telling, they are just counting this continuity equation and energy equation all along with momentum equation as the Navier-Stokes equation. You got my point, or anywhere you are getting doubt?
Yes, sir. Yes, sir.
You are getting?
Yes, sir. So in Navier-Stokes equation, we studied all three: the continuity, the energy, and momentum equation, right?
Right. So numerical analysis is used to solve this governing equation on a computational mesh. So previously I already told you what is discretization, like small, we will divide it to small domain, right? Small, we will
Yes, sir.
discretize it. Numerical analysis is used to solve this governing equation on a computational mesh. These things, this discretization is nothing but the mesh. Okay, this discretization is nothing but the mesh. Numerical analysis we used on this within this each and every cell we used to do. Okay, you got my point? This point, last point.
So these cells are in 3D, right?
Sorry.
When we mesh any object
Yes.
in Fluent or safety, so the mesh it creates it's in 3D.
Yes, it will be in 3D.
Okay.
See, this is the circle. Sorry, this is the cylinder. I understood why you get that out. This is the cylinder. Okay, 3D cylinder.
Yes.
If you are making a hexa, like a cube kind of structure, I said, is it possible for you to cover? Can you? Is it if there is a circle? You forget about that. There is a circle. Can you make a cube and close it, like all the area you can capture? Is it possible for you?
Oh.
If you are making cube, this portion will be remaining. You will not at all straight line. You will not at all make this straight line, because always there would be arc.
Yes. Yes.
Understood?
Yes, sir.
So for this, definitely you have to go to unstructured. Unstructured means if there is a circle like cylinder or anything, you have to go with the triangular. For 2D it will be a triangular, for 3D it will be rectangular. Okay, let me clear the screen and make it more good way. This is the circle. You can make like this. You can never make like this. You not at all. You can make. You see, this circle not should be. This is not straight line, of course. Okay, let me make. Here you cannot make cube. If you are making cube means there will be something there. There you can left. You got my point? But by making tria, you can. You can make small tria easily. It can cover. You got my point? Your doubt got clear, like
Yes.
3D and 2D that you were asking.
Yes, sir.
Okay, we'll see the some application of CFD where usually CFD is nowadays we are applying. Oh, we are applying in the aerospace or in mechanical engineering. We are applying where are the point? Oh, where we are using that I can tell. Aerodynamics, as you previously already asked. So aerodynamics, aircraft and its components, fixed wing, rotary wing, UAV, spacecraft, ground vehicle, obtain velocity, pressure, flow structure to get the forces because of the air movement and the movement force. All those things you can be calculate using the applying the CFD. In the power plant also you can use in the combustion. It is used in the internal combustion engines and gas turbines. In all those things it is used. You can go through. These are the pretty simple. Only the examples I have given. So when I will share the slide with you, you can go with it. So these are the some of the example I have given where you can use. Okay, you can go through it. If you have any doubt, any point, you can tell me. I can tell you how they are using there. Do you have any doubt?
Oh, no, sir. No, sir. Yeah,
So these are the point where we are applying. Let me close this. Okay. Some of the contours I have taken. So this credit goes to the NPTEL. So from the NPTEL website, I have taken. These are the contours, like some of the CFD simulations. So some of the IITs publication I have taken. So you can see flow over the flow over the aerofoil here within the combustion chamber. You can see this thing and we can move faster. Here also you can see the similarly the flow over the airfoil. This is how you can predict this is not the colorful. CFD is sometimes in the engineering field the people used to say colorful dynamics. Of course it is colorful dynamics, but you should know what color means what and how to optimize that color to some other color. That is the main idea. So these are in the ocean engineering, maybe on the over the ship, over the wind turbine, so over the designing a structure. Yeah, the structures. So this is where we are using. So here you can see in the wind turbine how the airflow patterns. So this is how. These are in the power plant, in the environmental engineering. These are the predicting the weather prediction. If you are making a very tall building, maybe how in the tornado if comes, how it behaves. If any some flow pattern around this building, you can predict to optimize your building strength. These are inside the nowadays you can nowadays computers are becoming the more powerful. A small very thin microprocessor can do a lot of work. When it is becoming very thin, it will generate a lot of heat. These heat should be dissipated, and you should know how much heat is predicting, and how where you should keep your fan, and so that your processor, your motherboard will work perfectly. You can see this image. So your flow pattern inside the motherboard, you can see. By that you can optimize your location of your chips and ICE, all those things, internal circuit, everything, your processor. So there it has been used. Okay, what are the, now we will come to, as you already looked, these are the fancy colorful images comes by which we can predict pressure, velocity, whatever the flow parameter we are looking. Now, is there only, now question comes, is there only CFD only way, or is there any other way also exist? So now here are the answer. You can go with conducting the experiment. Either you can do the experiment and you can get the result. Otherwise, you can do the theoretical analysis. Okay, you have the problem statement. Let us consider I have the pipe. I know I can use the Hagen-Poiseuille equation. There is a flow, inlet is there, outlet is there. I know the velocity here. I want to predict the pressure drop, all those things. I want to calculate the pressure drop. I can use the Hagen-Poiseuille equation and I can calculate. I have. Then what is the point? So we'll go. But there is a point. That is why CFD exists. I'll tell you in the next slide what is that point. And there is another approach, numerical solution. That is our best favorite CFD. So I'll tell you what are the merits and demerits of these equations. Sorry, these approaches. And these are the three approaches exist to solve the flow problem. Okay. What a 1 second. Yeah, experiment. When you are going through the experiment, what you see, what you believe. Means you did the experiment. You like you took a pipe, you gave the at 5 meters per second velocity, you just passed the water, and you found you got at some velocity some you got some at some velocity the liquid is comes out. It means it is definitely true for this much diameter. If you are giving at 5 meters per second, definitely it will, since there is no change in diameter. Let's make me the some another one converging. Okay, at 5 meters per second at some velocity it is coming out, v out. Okay, so you did this experiment, you got something, then you will definitely believe in that, right?
Yes, sir.
Often the most realistic way of, like this is the most realistic. If there is a aircraft, take the aircraft and do the experiment. But there is a problem. You cannot do that experiment over and over. You made such a big airplane. Its cost is huge. You did experiment, but it comes out to be some parameter you have to change to optimize. Then you will come and you will optimize again. You will do the experiment. How many times you will do? How much cost it will involve? You got my point? There will be lots of
Yes.
cost will be involved. Otherwise, in experiment, to reduce the cost, what we used to do, we used to do the wind tunnel test. In wind tunnel test, what we used to do, we make the scale down model. If my aircraft is, let us consider 5 meters. I am giving an example. If my aircraft is 5 meters, I will make it a scale down model. Okay, I will make a scale down model and I will take to the wind tunnel and will test it. But the problem with that in internal what comes, model fabrication and instrumentation are costly. When you will fabricate the model, that also costly, and to measure the all the pressure, temperature, and everything, you need to use some what those are called sensors. You have to use some sensors, and those instrumentation are very costly. Okay, many quantities may be difficult to measure. I am giving you an example. There is a ice engine. Okay, there is a ice engine. We when the combustion starts, okay, when the combustion starts, within a fraction of second, some physics is changing that you want to capture. Will you be able to? Do you have any sensor, anything to capture those changes? Within a fraction of
No,
second, it is happening. So it is very difficult when you are doing the experiment. But numerically, if you are solving, CFD can show you. You can tell at a point 0.00005 second what is happening. CFD can show you because you are modeling that one. Okay, that is the one of the good beauty of the CFD. Simulation matching of similarity. Huh? When you are doing the scale down model, there are many parameter you have to do the similitude. It is called like geometric similarity. All those similarity you have to maintain. So that also very difficult. Okay, it is not. I'm not saying it is impossible, but it is very difficult for a complex geometry to make similarity and similarity for the complex geometry. It is very difficult. Okay, so these are the problems comes in the experiment. So now there is another approach I already told you, that is called what? Theoretical approach, right?
yes,
So in theoretical approach, what you can do, exact or analytical solution of the governing equation. So previously I already told you what are the which equation we used to solve in Navier-Stokes equation. Sorry, in CFD, Navier-Stokes equation.
yeah, stop for sure. Yes.
But you know, Navier-Stokes equation till today there are no analytical solution are there for the Navier-Stokes equation. If you do, you will get the $1 million. Okay, from the Clay or there is some organization called Clay or something. They have that. There are I think seven or five problems are there. Out of that, an Navier-Stokes equation is one. If you can solve it, you can get $1 million. Anyhow, comes to the point. Solving that analytical, you have to solve this equation, which is pretty complex. Even though you are taking a lot of assumption and making it simpler and solving, that also very difficult. It is there, you can, but it would be very difficult. But in the real world problems are highly nonlinear. Okay, when it is highly nonlinear, solving it is mostly impossible. Okay, since the real world problems involves highly nonlinear, so solving it analytically is very difficult, sometimes impossible. See, already I told you, often restricted to simple geometry. If there is a we have, like if there is a flow in a pipe or flow over an cylinder, so these are the simple problems. So you have the analytical solution. When there is a flow over an aircraft, it is you can do. Over a cylinder you can, but over an aircraft you can do analytical solution. And assumptions which may not be very well cater to real world situations. I already told you, real world problems are highly nonlinear. You can assumptions, you will take a lot of assumption which leads to the wrong result. Like if your real result, like velocity should come 10 meter per second, the result will come maybe somewhere 1 meter per second, or maybe sometimes very much deviation from the real answer sometimes. Okay, so these are the demerits in the theoretical solution. Then next comes CFD. So these are the these are the drawbacks are taken care by the CFD. We'll see what CFD, how it takes care. So when do we use then CFD? When the theoretical solution does not exist. As I already told, the real world problems are highly nonlinear. So theoretic, we cannot solve it theoretically. Okay,
Yes.
then we will look for the CFD. So CFD comes into picture when there is no theoretical solution is available. If theoretically you can solve, that is the best way to go. There is not much cost involved. Only your intelligence is involved. Okay, and your answer would be very, very accurate. Experiments may be difficult to conduct or facilities do not exist. Like in the ice engine example I gave, within fraction of second, if something is changing, you do not have any facilities to calculate or to see visualize. So in that case, you have to definitely go for the CFD. Or experiment may be difficult. Like you can let us consider you are unable to do the experiment. In that case, you can focus on the CFD. What are the advantages of carrying out CFD simulation? There I have written, we can get high resolution numerical data in space and time. See, I am giving you an example of the ice engine. Within ice engine, you want at this point, this point, this point, this point, this point. If whichever point you want to calculate the velocity, pressure, temperature you want, you can calculate. Okay, if you are doing the CFD simulation, you can select, okay, at this point what is the velocity, it will show you. At this is the point, what is the velocity, it will show you. But let us consider you are doing same time you are doing the experiment. What will happen? How you do the experiment? If this is your ice engine, if this is your ice engine, you have to use some sensor. Let us consider you have used the sensor here, you have used the sensor here, you have to use the sensor here. Then only you can get the values at this particular location, not each and every point. You got my point?
Yes.
But if you are doing the CFD, you can get in each and every point. Wherever you want, you just in the answers print, you just right click, it will prove you the result. Okay, this is the velocity, this is the pressure, this is the shoot fraction, all those things. Okay, so this is the one good benefit. Like with respect to space and with respect to time, I already told you for the fraction of second you can see, but in here within fraction of second capturing is very difficult. And also I told you the space, how wherever you want you can see, but here only at the sensor location only you can see. Okay, we can get a, okay, flow parameter can be changed easily without additional expense. Okay, let us consider you have used previously, uh, you have given the in from the carburetor mass flow rate, you have given 0.005 kg per second. Okay, uh, so you have given 0.005 kg per second. Let us consider you did the experiment, you got to no, you are not satisfied with the result. Now you want, okay, now I will change, I will get the, I will do some another experiment with mass flow rate is 0.006 kg per second. Okay, then what will happen? There would be additional costs are getting involved. Like again, you are doing the experiment means again you have to make the prototype. Again, you have to give the mass flow rate. Again, you have to do the experiment. Yes or no? You
Yes.
have to again cost will be involved. But if there is CFD without any additional expense, only in the boundary condition you change. Okay, previously I had given the mass flow rate 0.005. This time you just only change this number 0.006. It will show you the result. Okay, if for the mass flow rate this type of physics will be developed. You got my point? There is no additional expense or anything. Only you have to only change and just give the simulation. You got my point?
Yes. Yes. Yes.
Okay. If anytime you are not getting or feeling bored, you just tell me. I can give the more example or good insight so that you won't feel the bored.
Yes.
Okay. So I already told you the Navier-Stokes equation. These are our favorite Navier-Stokes equation that are that mostly we solve in CFD. So the first one is the continuity equation. There are momentum equation in x direction, y direction, and g direction. There will be momentum in x direction, y direction, and g direction, and energy equation. If you can notice, You can see what are the variables in Navier-Stokes equation. And this is the density. Density changes with respect to time. So this is the time derivative. You can see these are the space derivative. Okay. In our upcoming lecture, I will tell you what these what these terms means. Okay, what this time derivative means. I will give you an example of a tunnel and I will explain very nice way in our upcoming lectures. For the time being, you just uh, understand there is a one time derivative, one space derivative. Yeah, so one property changes with respect to time, some property changes with respect to space. Then also in the momentum changes with respect to time, momentum changes with respect to space. And there is convection term. I'll tell you those convection term, what are those in the upcoming lectures. And this is the pressure gradient term, and these are the non-dimensional numbers. That also I will tell what is the benefits of keeping in the non-dimensional form. Then these are the stress tensors. Okay. In the upcoming lecture, it would be more clear. Or after doing the derivation, for the time being, you just you just know this much for the time being. You should have the knowledge what are the terms like time derivative, space derivative. You have. Okay. You see those equations. So what are the features of these equations that I have told in the here? The equations are complex. Yeah, it is obvious. The equations are complex, and I can tell they are set of partial differential equations. Of course, these are the partial differential PDEs, and they are coupled equation. What do you mean by this coupled equation? Coupled means you cannot solve this continuity equation alone. You need the help of momentum equation to solve the continuity equation. That is why it is called the coupled equation. Okay, both the equation has to solve simultaneously. Then only you can solve. You can get the parameters. Okay, properties. They are nonlinear. From the engineering mathematics, you might have known what is the why you how to define a PDE is nonlinear or linear. So if you closely look into the Navier-Stokes equation, you can easily understand it is a nonlinear equation, because there is a u comes, velocity comes also. Again, derivative comes with the del u. So it is again function of the velocity, del u by del x. Then they cannot solve analytically, and that is the main reason why we are going for CFD. I already told you, first we will prefer analytical solution. If you are not getting analytical solution, then go for the CFD. And I already told you, till today Navier-Stokes equation do not have any analytical solution. Okay, if you can solve, you can get $1 million US. That is why we are using CFD. Okay. Then while doing the CFD analysis, what are the steps we usually involves? What are the steps we usually follow? First, you have to understand the problem definition. These are the procedures you should follow. Whenever, let us consider tomorrow you are getting a job, someone came and gave you the problem. Okay, take this and do the simulation and give me the result. What are the procedures you should follow? You have to follow the problem definition and the objectives of performing CFD simulation. Like you have to understand what are the parameters the vendor is looking from you. Otherwise, if you are alone doing the analysis, you should know what are the parameters we are looking for, and you should have the clear-cut idea of the problem definition. Then you have to clear the geometry configuration. Clear the geometry. When you are creating the geometry, it should be clean. When I am saying clean means there should not be any error. When you will move to the ANSYS print or open form, that time you will have the more clear-cut idea how to clean a geometry. Okay, and what do I mean by clean card model? See, till now, whatever I taught, I know at many point you must have the doubts, and these things will be clear by the time you will be ending with the course, and by the time you are using the ANSYS Fluent. Now, since you are starting, many points would be bouncing over your head because you for the first time you are getting into this knowledge. Okay, so
Yes.
don't be hurry. You keep patience. By the time you are just end the assistant course, again come back and read these slides. You can easily, very easily, you can understand, and at that time you can appreciate. Okay, these are the things. So now definitely some point would be bouncing over your head. I know it will definitely happen. Create clean card model and split into meaningful domains. Let us consider there is a carburetor. Okay, this is your carburetor or injector in your bike or car. You want to do the simulation. You want to see when you are giving the air and the fuel are coming, and they are mixing here at certain air fuel ratio, and it is coming to the your combustion chamber. Okay, you want
Yes.
to see the how the flow comes, whether it is coming like a spray or it is coming like a directly small droplet, how it is coming. So in order to do that simulation, you have to what you have to do, you have to create first your carburetor. Okay, then you have to create your combustion chamber, right?
Yes.
When you are creating a carburetor, okay, when you are creating a carburetor, what I told here about, you have to create a clean card model, means these cards should not have any error. This card geometry, when you are making any card geometry should not have any error. And you have to split into meaningful domains. Meaningful domain means you have to tell to the CFD that here your air fuel mixture, sorry, air fuel mixture would be mixed. So this is your one domain. Okay. Here, this is your another engine chamber. It is your, this one is your domain one. This is your domain two.
Yes.
Okay. Then only fluent can understand and it can be easily done. If you are entirely making, okay, this is my carburetor, this is my chamber, and entirely one geometry, fluent can't understand. It will give you the problem. In your result, we'll see when you will do the ANSYS fluent. That time I will show you. I will make this error. I will show you what are the possible errors might come if you are making this type of mistakes. Okay, understood? Okay. Then choice of governing equations, like what are the governing equation you have to choose, that you have to understand, you have to take first. And approximation, what are the assumption you have to take. So estimating the thermophysical properties. When you are giving, again, take that air fuel mixture carburetor problem. This is your carburetor. This is your heat chamber or combustion chamber, heat engine. When you are giving, when you are allowing the fluid to come out, come to the your air fuel mixture to come into the heat engine, you have to calculate the thermophysical properties, like what is the density, what is the mass flow, density, then viscosity, all those properties you have to give correctly. Then only you will get the correct result. At the end, your equation depends on the properties only. Instead of for petrol, if you are using the diesel, there would be result would be something different. Yes or no?
Yes.
So for a diesel, there would be different pressure, sorry, different viscosity, different density, like that. You have to calculate the proper thermophysical property and correctly you have to give, so that you can get the correct result. Okay, that is also important parameter you have to look. Domain definition. Domain definition and discretization means these are comes under the pre-processing step, like meshing. So these are domain definition, as I already told you. You have to give the, this is your domain one, this and this is your domain two. Then only it can properly understand. Then you can move to method of solution, governing equation, like partial differential equation, whether you will use the finite difference method or finite volume method or finite element method, which one will give you the correct result. You have to choose that one. Mostly most of the current days commercial software, they are using finite volume method. So we will be in our entire course, we will be focusing mostly on the finite volume method, and in the MATLAB course, we will be focusing on the finite difference method. Then we will be using analysis of the result and validation. Once we got the result, we will validate it. That process is called as post processing. Once you got the contour, you will visualize it. See, at the end, CFD will give you bunch of data, pressure, velocity over entire domain. It will have a lot of data. But how you can visualize? You need some contours, like in the somewhere you can see the red, somewhere the green, yellow. From those contours you can see, okay, at the red region here from the color bar, you can see, okay, temperature is something. By that only you can notice, okay, here some within this range the temperature is coming at this location, that location, what are the values. You might have noticed the colorful images.
Yes.
Yes, in the colorful images what you saw, red means there would be some when here is red, in the color bar you can see some red region would be there, and some values would be written. It means this region belongs to this values. Okay, so these are by looking those you can analyze, and these process this step is called as post processing. Okay, so these are the steps usually involved in CFD. Like when you are getting any problem statement, these are the steps you will usually follow. Okay, references that I will tell you to take. So these are the books I will suggest you to go through, and I will also follow these books. So these are the books I will highly suggest you to go through, so that you can understand in depth the CFD. And if you have any doubt, you can ask me. And I will also following this book throughout the course. And also the two more books are, I forget to mention. I will send you through WhatsApp. One John D. Anderson, written by John D. Anderson. Another
J.D.
one is J.D. Anderson. Another book was written by Hostis and Malala Sekara.
I have the J.D. Anderson one.
Yeah, that is the nice book. That was okay. Conclusion. So finally, what we conclude for the CFD? CFD has innumerable application in problems involving transport phenomena. When I am saying transport phenomena means like fluid transport. Don't transport means don't think on the truck or any bike. Of course, when truck or bike moves, there is some fluid flows over that bike. Yeah. So this transport phenomena, CFD application is problems involving the transport phenomena. CFD is often performed to solve the problems which are difficult, if not impossible, to tackle using experimental and theoretical approach. So this point also I have explained. There are several steps involved in CFD simulations. The best way to understand the steps would be to develop computer program on your own for comparatively simple model problems, and following every steps from problem definition to post processing the results to be actively participate in the excitement that waits. Might be this statement made you bored. So here only point I am saying, see, commercial softwares are there, you can easily do, but I will suggest to write some codes by your own and understand what is CFD. That is the main motto that from the beginning I told, and here also again I mentioned. That is the whole sentence means. Okay, I have taken one case study to show you how the CFD really helps in the real life. See, the problem in heavy duty truck. Previously, you might have seen in the United States, if you go, 70% of the oil is used for the transportation. Like from the transportation point of view, like carry the goods, 70% of the oil they are using. 20% of this is used by the heavy duty truck. Okay, heavy duty truck are they are taking 20% out of that. So these are the fuels. Okay, in the next slide it would be more clear. See, okay. Do you have the idea of a CD, coefficient of drag?
Little bit.
Okay, that much is okay. See, whenever over the car drag coefficient increases, if your
Yes,
drag
sir.
coefficient, aerodynamic drag coefficient increases for an any truck or any automobiles, you can see the how much horsepower contribution increases. Like this much, this much energy you have to provide to
Yes.
overcome. Okay, whenever they are this much see, after some time rolling, these are the rolling friction and accessories. In the next slide it will be more clear. See, aerodynamic drag, if it is increasing, your speed is, see how it is decreasing. See, this is the speed. If this one is increasing, you can see the plot. In the next slide it will be more clear. So see, these are the aerodynamic drag. See, the wherever you are seeing this type of color, it is because of the pressure drag. These are the target areas where they can modify. And how they came to know? They came to know by doing the CFD analysis. They calculated the CD by doing CFD analysis. Okay, here CD is 0.2, here from the tire it is coming 0.05, here 0.05, from the front you are getting 0.2, like that. And these are the target areas where they try to modify. So these are the in the beginning days. These trucks are in the beginning days. Nowadays, if you can see the trucks, I will show you. See, this is how I have taken from the NASA photos from NASA uh, uh, NASA website. So you can see from the beginning how they have developed. See, as they have did the without CFD analysis, it would be very difficult to find out where to modify so that a drag force would be less. And by doing this CFD analysis, they can understand, okay, these are the location how much CD is developing, these are the location how much CD is developing, at different location how much CD is developing, so that they started to optimize. See, this is the procedure they followed. See, nowadays you can see the goods carrier are like this. So if they will do the same thing, like calculate the CD and optimize their model, they had three options. Either they can do the wind tunnel test, they can do the road test, or they can do the CFD test. They can do the CFD. If they are choosing for the wind tunnel, it would be cheap. Okay, little bit cheap, but disadvantages would be accuracy. Okay, at the end, wind tunnel is the not real case. Wind tunnel is the you are inside the wind tunnel you are testing. Okay, it won't be very much accurate. You can opt for the road test. You can take your vehicle, you can on the road you can test, but it will be very costly. How much fuel will be involved, how much manpower will be involved, and it will be very lot of time it will take. Okay,
Yes.
now another option comes for us, CFD. If you are choosing CFD, just take a computer, create a cad model, do the simulation. Okay, and it will be very cheap. No need to create any automobile or any goods carrier. You have to only create a cad model and you have to run. So it is very cheap. This is the big advantages. And but the disadvantage is confidence in the result. The result you gave, whether is it correct or not, how one can trust in your result. So next thing come, how can one can trust. So trust of your CFD result comes from the performing experiment and validate. Okay, so performing experiment and validate. So the whole idea is how the main thing is coming, how you can tell that okay, my simulation result is correct. So procedure is, you do CFD analysis, you predict something. Okay, CD is, let us consider you predict 0.5. Okay, let us consider you predict this CD. Now for the same model, you create a real goods carrier. Okay, create a real goods carrier, do the experiment and calculate CD. Okay, try to validate. If it is exactly matching with 0.5, then you can understand, okay, now whatever the model CFD model I had created, it is matching. Now no need to do the experiment. I can only change my card profile. Previously the geometry is like this. Now I can made one thing. I can make like this. I can made like this. Now I can do the simulation, not the straight. Now I can trust on my results. Okay, finally I optimize, then I can do the final experiment. Within from the, transforming from this to the final product, like final aerodynamic shape, let us consider what would be final aerodynamic shape. The middle, in the middle, if you are doing experiment, many model you might have done. If you are doing the real experiment, these thing now obsolete. You can save the cost, and now finally you can make the product on the, you can do the experiment on your final product and you can validate. You got my point?
Yes, sir.
Or you have any doubt?
No, sir.
So this is the whole idea of the CFD. This is how the CFD works. So this is for the with this I conclude for today. If you have any doubt, you can ask.